Good day everyone. So in this video I am going to solve problem from the Strength of Materials 4th edition by Ferdinand Singer. I think this is under shear stress. So the problem: compute the shearing stress in the pin at B where a member supported as shown in the figure. The pin diameter is 20 mm. So we are given with the pin diameter which is 20 mm, and we are to solve for the stress in the pin. So in order for us to solve the stress in the pin, we have to calculate the reaction force acting in the pin. So let's start by making the FBD of the system. So we have here upward RBV. This is just an assumption, but we know that there is a vertical force or a vertical reaction acting there, since that is a pin connection. And also we have a horizontal reaction force which is RBH, and also we have a vertical reaction at this roller. So we also have this 40 kilonewton inclined at 35 degrees with respect to the horizontal. So in order to calculate the stress in pin B, we have to solve for the magnitude of the reaction force acting at the pin B. So since we are given the diameter of the pin, and we have this vertical and horizontal component of force RB, we can get its resultant, and that resultant will use that in order to get the stress in the pin B. For this problem, we can summate forces along vertical and horizontal equal to 0. Also, the summation of moments at any point is equal to 0. So we can use the summation of forces along vertical and horizontal equal to 0. Why 0? Because we want this system to be in a static equilibrium and we don't want it to move. And we want to calculate the stress of the pin that will make the system static or in static equilibrium. So I have resolved the force P into its component. We have P cos 35 for its horizontal, cosine since this is adjacent to this angle, and P sine 35, sine because opposite to the angle. So solution: summation of forces along horizontal is equal to 0. We take positive to the right, so P cos 35 minus RBH is equal to 0. We only have two forces that are in our horizontal. So P cos 35 positive since it's going to the right, and minus RBH since we assume that it's going to the left. So RBH is equal to P cos 35. Substituting the value of cos of P is 40 kilonewton. So RBH is equal to 40 kilonewton cosine 35. So that is approximately 32.766 kilonewton leftward. So therefore our assumed direction is correct since our answer for RBH is positive. So it is truly leftward. So now we want to eliminate the force RC because it is a known force, and I think it would be easy for us To solve for RBB, if we will take summation of moment along point C, because this RC will will not cause a moment about C, since it's it's its line of action will hit that point C. Also for this RBH, it is also along C. So we set clockwise positive. So RBB times 250. RBB causes a positive moment times its perpendicular distance, 250 mm. And P cos 35 times 200 mm. Its perpendicular distance about C is 200 mm. Plus P sine 35, and also times 250 mm. It also has 250 mm of distance about C. So substituting the value of P and manipulating the equation, we now have RBV equals to negative 40. So I just factor out negative 40 here. So dividing both sides by 250 mm. So the value of our RBV is negative 49.156 kilonewton downwards. So negative, that means that our assumed direction for RBV is incorrect, or the true direction of RBV is going downward. So now we're going to solve for the magnitude of the RB. So RB is equals to the square root of RBV squared plus RBH squared. So substituting, so we found out that RB is equal to 59.076. So from the definition of shear stress, tau is equals to V over A, which, or shear stress, is equals to the shear force over the sheared area. Since the only force that will cause the shearing is RB, so we will equate RB is equals to 2V. Why 2V? Because this is a double shear. So solving for V is equals to RV over 2, right? So tau is equals to RV over 2 over A, where A is the cross-sectional area of the pin. So RV is RV over 2A. So substitute, and 59.076 times 10 to the negative 3, I make this Newton for us to get a final answer of megapascal, since Newton per mm squared is megapascal. So the final answer is 94.022 megapascal.